and I will also start recording, and I think we may let the others to come to the meeting, right? So we are
Yes,
ready.
sir.
Okay, yeah. I will admit all, and then I will make sure that the so within it we'll wait another few minutes, and
Sure.
yeah.
Just message me if you experience any difficulties in hearing or something like that. I'm at home, so.
So within it we have 2 minutes, so we'll wait.
Sure.
Additional 2 minutes. Hello, good evening to everyone, and welcome all to the webinar of the IEEE Signal Processing Student Branch Chapter of the University of Moratuwa. So this is the fourth webinar of our annual webinar series, and today we have the webinar on the ultra broadband signal processing using radio frequency system on chips for terahertz communication network. So nowadays mainly people are talking much about the 5G work, fifth generation wireless communication, and the world is moving to the sixth generation and the communication above 100 gigahertz. Actually, the uh, a part of the spectrum we have not used so far, mainly for the wireless communications. So today our guest speaker is Dr. Vidunet Aryaratna. He's a colleague of me. I have worked with him and his advisor, Professor Archana Madanayaka, for several research work. So Dr. Vidunet Aryaratna is currently an associate research scientist at the Institute for the Wireless Internet of Things at Northeastern University, Boston, USA. He completed the BSc in Electronic and Telecommunication Engineering from the University of Moratuwa in 2013. He received the PhD degree in Electrical Engineering from the Florida International University, USA in 2019, focusing on low complexity multi-beam beamforming circuits for millimeter wave communication systems. From 2013 to 2014, he worked for at Trent Lanka, now acquired by the Synopsys Incorporation, and he spent the summer of 2018 with Cisco Systems, working on FPGA accelerators for IEEE 802.11 networks. His main research interest includes software-defined radios, one and multidimensional signal processing, RF systems, and high-speed modem design. And he is currently working on a project related to the sub-terahertz, or basically the millimeter wave frequency communications. So I would like to invite our guest speaker, Dr. Vidunet Aryaratna, for his presentation. Vidunet?
Thank you, Dr. Shamir. You can hear me, right?
Yes, yeah, we can clearly hear you.
Okay, good evening to everyone. I'm Terahertz, as Dr. Shamir produced. So I'm an associate research scientist at the Institute for the Wireless Internet of Things at Northeastern University. Today I'll be talking about ultra broadband signal processing in general, and specifically using radio frequency systems on chips for terahertz communication networks. And I would like to welcome all of you, especially thank you for allocating your Sunday evening to joining for this. And first of all, I'd like to thank Dr. Chamira and the organizing committee for inviting me to do this presentation. This will be the outline for my talk. I'll start with a brief motivation, which is ultra broadband terahertz communication. And then I'll introduce you the ultra broadband networking systems testbed here at Northeastern University, and present you some recent experimentations that we have done above 100 gigahertz. Then I'll come to the Xilinx RFSoCs and their architecture, which we have used for our proposed backend that supports multi-gigahertz of bandwidth. And then I will present the vision and the proposed backend architecture to you, and then come to the RFSoC-based prototype implementations here that we have here, and some early experimentation results. So over the last few years, wireless traffic has drastically increased due to the change in the way we create, share, and consume information, and it is expected that more than 13 billion mobile connected devices will be available by 2023, and this is going to create a huge data rate capacity requirements, and we would need much faster connections. So when looking at the past decades, we can see that wireless data rates have doubled every 18 months over the last 30 years, and 5G networks which have been rolled out now are promising data rates at about peak data rates about 20 gigabits per second right now. And once these front-haul networks become faster and faster, there should be much larger pipes at the backhaul links to accommodate these faster data rates at the front-haul networks. So the prediction is that we would be needing terabits per second links, and that will become a reality within the next 5 years. So the next big question is, how are we going to achieve that? So obviously one solution is to have more bandwidth in our system. And then the next question is, where do we find this bandwidth? Okay, so if we consider this frequency spectrum axis from 0 to maybe beyond 10 terahertz, we know that all these legacy wireless applications that we know, radio, TV, cellular systems, Wi-Fi, all these, I would say, majority of them are confined to sub 10 gigahertz, I would say, but everything up to 100 gigahertz is currently allocated. So if we are searching for more bandwidth, then there is this optical frequency spectrum, which has a sort of bandwidth where we can jump into if we are in search of more bandwidth. But there is this terahertz band from 100 gigahertz to maybe around 10 terahertz, which has not been much explored for wireless communication systems. So the terahertz band is primarily occupied only by the passive sensing community for now, and moving to terahertz frequencies will provide sufficient bandwidth for next generation wireless networks to achieve data rates demands for the next generation wireless systems. The terahertz communication is envisioned as a key wireless technology for the next decade and a major player in the 6G systems and beyond. So moving to terahertz frequencies will open up a plethora of applications. So we'll be having terabit wireless wires that will enable very fast links for personal area networks, very fast local area networks, and people envision terahertz links to be enabling high-speed, long-range backhaul links for enabling internet connectivity for rural areas. And also terahertz frequencies have favorable propagation characteristics in the space. So this will enable terabits per second backhaul links in the sky, which will enable very high-speed internet access for across the globe. So now, people say that terahertz channel is horrible, so why would we want to go there? But of course, terahertz band provides a huge transmission bandwidth, but that comes at a cost of very high path loss. So there are these, so in this figure, I have the loss across versus the frequency. And you can see that these solid lines represents the absorption loss and the dashed line represents the spreading loss. There are these frequencies where, I mean, when there is terahertz radiation, it resonates with the water vapor molecules, and that absorbs, and that accounts for absorption loss. And there are certain frequencies in this band that has a very high absorption loss. So if we pick the transmission frequencies smartly, then we can accommodate, and I mean, we can leverage these huge bandwidths within these absorption bands. So the other aspect is that now we are talking about terahertz frequencies, and we are talking about very small wavelengths. So with the very small wavelengths, if we look at the phase space path loss equations, you will be seeing that because of the effective antenna aperture at these frequencies becomes very small and small, the power that is intercepted by the antennas for a given power density will be very minute. So therefore, you will be having a lot of spreading loss, and that can't be avoided when you go higher in frequency. So we would need to take care of these spreading losses to to compensate and close the link projects. So we would need highly directional antennas, either fixed or very high dimensional antenna arrays. So now the next question comes that can the terahertz band actually be used for wireless communications or experimentation? So it has to be noted that the spectrum up to 275 gigahertz is, as of today, fully regulated and been allocated by the International Telecommunications Union, and correspondingly in the US by the FCC. So within this 100 to 275 gigahertz band, there are bands assigned to different services, including fixed and mobile communication systems, satellite space links, and also there are these scientific bands in which no emission is allowed, which are primarily used by the passive sensing community and radio astronomy community. And among these allocations, there is this 122 to 123 gigahertz band and the 246 to 248 gigahertz band, which have been marked as ISM bands for use with industry, scientific, and medical experimentation. And Also, there is a lot of initiative in the US for opening up these bands for wireless communication and experimentation. And specifically the US SSC Spectrum Horizon program has enabled access to more bands for unlicensed operations, namely these particular bands. And this corresponds to freeing up a total of 21.2 gigahertz of the spectrum for unlicensed operation. So if we look at the recent advances in terahertz communication, so we can identify a lot of significant progress in terms of enabling communications at these frequencies. So mainly there is a huge progress in the devices from the devices side, from electronic, photonic, and plasmonic perspectives for enabling communication at these frequencies. And there's also considerable work that has been carried out for theoretical modeling of the terahertz channels and experimental measurements of the terahertz channel. And physical layer solutions that leverage the behavior of the terahertz channel has also been developed, but there is very little experimentation validation that has been taken place. And there is absolutely no terahertz network level demonstrations that has taken place at least for my knowledge. So therefore, testing of the different signal processing, communication, and networking solutions will require the development of new simulation and experimentation platform. So there exist a few experimental testbeds that cover different parts of the terahertz spectrum, for example, 120 gigahertz, 240 gigahertz, and etc. So talking about the terahertz testbeds, for the time being, most experimental platforms have been designed with the purpose of ultra broadband channel sounding or initial physical layer testing. The testbeds are confined to static systems. That means when I say static systems, they utilize a high-end arbitrary waveform generator at the transmitter and a high-end digital storage oscilloscope at the receiver side that can handle ultra broadband bandwidths. So these particular testbeds rely on MATLAB processing, but they are very convenient to try out new ideas, new waveforms, and new algorithms in physical layer. So just to give you an understanding of how these platforms look like, so this is the ultra broadband networking systems terahertz testbed at Northeastern University, where I work. And this particular testbeds consist of two main subsystems, the front ends and the digital backends. So there are three major front end nodes that supports three major frequency bands. One set at 120 to 140 gigahertz, another set at 200 to 240 gigahertz, and another set at 1.0 to 1.05 terahertz. And we have two main signal processing backends, the offline system that consists of the AWG and DSO system that supports 32 gigahertz, and also this real-time software-defined radio backend that supports 2 gigahertz. So when talking about the front ends, the main work of the front ends is to generate, upconvert, and radiate the terahertz signals at the transmitter side and at the receiver side to detect downconvert signals to the RF frequencies. So the main technology that enables generation of EM waves at these frequencies is the use of frequency multipliers. So these are some specifications of the nodes that we have here. So if you look at this 120 to 140 gigahertz front end that is by Virginia diodes, it uses this 4x frequency multiplier chain to start with a 30 to 35 gigahertz LO input to go into this particular frequency. And for the 1 terahertz system, it uses a cross 24 multiplier chain to start with a 41 to 43 gigahertz LO input to multiply up to 1 terahertz. And as you may see now, when we go to higher frequencies by frequency multiplications, there are a lot of harmonics being generated, and therefore, higher the frequency we go, we will have less power. And therefore, currently, a lot of research is being done to make high power devices at these particular frequencies. Just to give you an idea of how these devices look like, these are the three front ends that I was talking about, and we are using very high directional horn antennas for closing the link budgets for long range communication. And they are also sometimes equipped with lenses. For example, these two antennas And these actually provide about 40 dBi gain. Getting back to DSP backends, so we have this offline 32 gigahertz system based on the state-of-the-art arbitrary waveform generator that supports 32 gigahertz of bandwidth at a sampling rate of 93.4 gigasamples per second. And at the receiver side, we have this DSO, which can support a whopping 63 gigahertz of bandwidth at a sampling rate of 160 gigasamples per second, so which is very state-of-the-art equipment. And this setup provides fast transition from mathematically and digitally described signals to analog baseband intermediate frequency signals. So the other digital backend option that we have is this real-time commercial transceiver system that implements the full physical layer. This is the National Instrument-based millimeter wave system, which is how they market this. So this supports 2 physical layers. The single carrier physical layer supports up to about 1.7 gigahertz of bandwidth, and the OFDM multi-carrier system supports 800 megahertz of bandwidth. And going for some recent experimentations now, this figure shows a 35 meter link that we demonstrated across the hallway of the building using the offline 32 gigahertz DSP backend. So the near end shows the AWG, and the far end consists of the DSO-based receiving backend. And we were able to generate or demonstrate different, links at different bandwidths and using different modulation schemes. Using both the 120 gigahertz system and the 240 gigahertz system. So this Constellation Output shows you that this is actually the pre-equalized constellation, and you can see that from the constellation, although people think that there is not multipath propagation at these frequencies, there is actually a few multipaths, and the constellation after post-equalization looks very good. And these are some experimentation results done at different modulation schemes, different distances with different bandwidths, and I'm not going into details, just showing for the sake of showing the experimentation results. And these are some recent experimentations done with the real-time software-defined backends that supports 2 gigahertz. So we were also able to generate now, because this supports a full stack implementation, we are able to generate throughput results so with different modulation and coding schemes, and these are yet to be published. So going back to Terahertz testbeds, although these commercial software-defined radios exist with real-time digital backends, these baseband bandwidths that are supported by these nodes are limited to less than 2 gigahertz, and they do not facilitate greater bandwidth supported by the front ends at terahertz frequencies. And now the ultra broadband devices are ready. Comms aspects are also being figured out, but it's still not clear how will the real-time processing of ultra broadband signals be handled at these frequencies. So in order to advance terahertz communication research, there is a tremendous necessity in developing SD hardware and architectures that can support the terahertz frequencies and process digital baseband bandwidths to tens to 100 gigahertz of bandwidth that can make use of the greater bandwidths available at the terahertz frequencies. Otherwise, there is no point of moving to these frequencies. But there are a few challenges and limitations, and that's why such digital backends are not available currently, because we know that from the Nyquist sampling theorem for processing a B bandwidth system, we would need to sample the signals at more than 2B sample rates. So this means now for when we say ultra broadband signals, we are talking about signals that have 10 gigahertz or approaching 10 gigahertz of bandwidth. So this would need very high speed data converters able to support multi gigahertz of bandwidth. And on the other hand, even though we have data converters that sample at these frequencies, we should have digital hardware that is able to cater these data converter speeds. So the fastest digital platforms we would think of would be coming from an application-specific integrated circuits designed at very low CMOS node. But now ASICs are much far because now still the terahertz communication technologies have been figured out. So it's not the time to think about ASICs. Now what we need as of today is programmable digital hardware capable of handling these ultra high speed sample rates. So when we look at the state of the art in RF digital programmable hardware, we can see that in 2017, Xilinx released this breakthrough architecture of the first radio frequency system on chips, integrating the data converters on the same SoC as the programmable logic. And this, the significance of these devices is that the data converters can support up to a few gigahertz of bandwidth, and this enables the integration of many converters on a single chip, providing increased channel counts within a much smaller footprint. So in the figure, figure in the left shows a conventional SoC architecture where you have the processing subsystem, the FPGA fabric on the same chip, and the conventionally what is done is to externally interface the data converters through IO, through serializer IPs, to connect these guys to the SoC. But what they did in the RFSoC structure is to bring in these data converters into the same chip and monolithically integrating all of them into same silicon, thereby reducing the external interfaces, and that leads to reduce of the system power consumption and reduction of these serializer IPs. And by doing this, they were able to get much faster sample rates as well. So if we see the Xilinx RFSoC today, they provide multiple, when I say multiples, 8 or 16 data converters integrated into single chip where each channel can support a few gigahertz of bandwidth. The Xilinx ZU28 DR chip, which is a much popular chip, supports 8 DACs at 6.5 gigasamples per second and 8 ADCs at 4 gigasamples per second. And as if you look at this particular device, in overall, this chip supports a total of 16 gigahertz of bandwidth across all channels at the ADC side and 25 gigahertz of bandwidth at the DAC side. So now these RFSoCs have gone through 3 generations, and the newer generation is Gen 3. So if we look at this particular device, it can support 10 gigasamples per second at the DAC side, and they have 16 of them available in the chip. So this corresponds to 80 gigahertz of bandwidth supported by the whole chip, which is very significant. And the RFSoCs have been primarily used for 5G research and development, specifically for MIMO and phased array implementations. So here I show you some Xilinx evaluation boards for the RFSoCs. I'm not going to go into details, and there are other evaluation board options from other different vendors as well. We are using this high-tech global board because it has a smaller integration and single-ended outputs, both on DACs and ADCs. So our vision and approach. So our vision is to use RFSoCs to realize a new digital backend able to real-time process ultra broadband signals. And the approach is to design and implement a frequency multiplex to multi-channel backend architecture able to support multi-gigahertz wide signals. And this would incorporate having 2 main subsystems, digital system design and implementations of baseband processing targeting the RFSoCs, and analog IF network design and integration for frequency multiplexing and demultiplexing of the channels. So this slide shows you an overview architecture of the real-time multi-channel digital backend architecture that we have proposed. So the main idea is to use each of high bandwidth data converters of the RFSoCs to process independent channels, and we are using this ZU28 8x8 chip, and then to multiplex multiple channels to produce multi-channel aggregated IF. Now, here's subfigure A shows you the architecture of the transmitter side, and we are using this 8-channel RFSoC chip. So we are envisioning to have 4 simultaneous baseband processors and use 2 DACs to bring out I and Q channels out in analog form, and then to use a set of IQ mixers to uniquely to put these baseband channels at specific IF frequencies, and then use a wideband combiner to produce a fat IF ultra broadband signal. And now at the figure B shows you the receiver architecture, one possible realization of the receiver architecture. So given that we have this number of channels multiplexed in the transmitter, we would have to split the signal to that amount of channels and then use a direct conversion receiver architecture to bring each channel down to baseband again, and then parallelly simultaneously process everything and to process the whole ultra broadband bandwidth signal. Now, there are other specifics of the testbed that we are doing, but I'm not going to go into details of that. So there are a few considerations from the analog network side. It needs an individual oscillator per baseband channel because low-end oscillators have higher frequency offsets. This can be a problem. We are using a lot of oscillators. And frequency multiplexing must be designed such that minimum interference is caused by the harmonics. This has to be addressed as well. IQ mixers in general have a high conversion loss, therefore link budget needs to be planned carefully. Of course, more the components, higher the noise flow will be. So this network has to be properly designed with the proper components. And when talking about digital implementations, the main consideration is that the clock rates that the programmable digital fabric can handle are lesser than the data converter sample rates. So for a high-end FPGA that implements a modest design, we are talking about 400 megahertz of maximum maybe clock frequencies, and the data converters we are talking about 4 gigasamples per second, so which is a order of magnitude difference. So the rate from the data converters should be matched to the digital processor speed to process everything without loss of information. Therefore, we need polyphase digital architectures in digital which can process multiple samples at a single clock edge. So when I say phases, it refers to the number of parallel samples being processed at once, and the number of phases M in the digital design is determined by the data converter sample rate R and the digital logic sample rate P, such that R equals P times N. M, I mean, when the number of phases in the design increases, the digital hardware consumption also increases by a factor of M. I mean, I have illustrated this concept in this particular figure. So for example, consider a receiver side ADC sampling at R gigasamples per second. So if your digital can only support the P gigasamples per second rate, then you would need to process M samples such that M is R by P. So if you have a conventional FIR filter, for example, in a conventional system where sequence samples are coming, then you would only need one FIR filter, you will be done. But since we are processing M samples at a single clock edge, now we would need M parallel copies of these filter to process the whole bandwidth without any loss of information. So the inputs to the filters have to be properly organized, and you can figure it out when you look this carefully. So the other main aspect is the choice of physical layer parameters. So the terahertz channel itself is not necessarily frequency selective. The channel is considered to be sparse because there are not much multipath propagation, and also we operate in between the absorption lines. Therefore, not much frequency selectivity come from the terahertz channel itself. But significant frequency selectivity does come from the frequency responses of the ultra broadband front-end devices, because these front-ends supports a lot of bandwidth. They have very high frequency deviation in the frequency response. Therefore, to tackle this, an OFDM-based physical layer is selected to make the equalization easy at the receiver. So we are doing 4 gigasamples per second at transmitter and receiver. So this is the minimum of the maximums that the ADCs and can support for the chips that we have chosen. So this allows 2 gigahertz of real bandwidth per channel, but this is the critical Nyquist frequency, but we can't use the full Nyquist rate as it increases the demands of analog anti-imaging and anti-aliasing filters. Therefore, 2x interpolation at the transmitter and a 2x decimation at the receiver is used. So the configuration. Okay. So Pamit is saying that if you have any questions, you can ask them through the Slido link that is being posted. So the configuration would support a total of 8 gigahertz of bandwidth in the current system. And we have selected the number of subcarriers to be 64 subcarriers and for the 2 gigahertz wide channel. So each subcarrier will support a bandwidth of about 32 megahertz, and this is wide enough to consider the channel to be frequency flat for our front ends. And we are using this 802.11a like physical layer, especially because it uses a 64 point FFT size and has a relatively simpler frame format. So diving into the details of the transmitter side implementation. So it's a conventional, more or less a conventional OFDM systems that supports 64 subcarriers and also supports most of the conventional modulation schemes starting from BPSK to up to 64 QAM at subcarrier level. And the symbol rate is 2 gigasymbols per second per channel. So the digital backend can support up to 12 gigabits per second per channel. And digital circuits are implemented in a polyphase structure with 16 phases. So this figure shows you the conventional FDM processing architecture. The only difference is now we are doing a much higher bandwidth than a typical Wi-Fi channel. And also because of the higher bandwidth, we would be needing to do this polyphase structure that makes the digital hardware a little complex. And we are using this particular packet structure with a preamble that consists of a short training field and a long training field. Short training field is responsible for start of packet detection, frequency offset estimation, and long training field is used for channel estimation, FFT timing acquisition, and stuff like that. And here I show the real and imaginary parts of the waveforms that we have used for the short training field. And it's derived from 12 non-zero subcarriers. So I'm not going to go into details. I'm just showing them here. And this is the long training field, and these are the real and imaginary parts, waveforms. So this is derived from 52 non-zero subcarriers, which are BPSK modulated. And so after building these circuits, digital circuits, we have to verify this transmitter prototype is working correctly. So now we have a 2-channel prototype here, sending 1 channel BPSK modulated and the second channel QPSK modulated. You can see that in the frequency domain, it has 2 channels with each having 2 gigahertz of bandwidth, making an aggregated 4 gigahertz bandwidth. Now we were able to capture these waveforms in the software, the oscilloscope, and then software process it, and we were able to lock the constellations with EVM of close to minus 20 dB at channel 1 and minus 17 dB at channel 2. So moving on to the receiver side implementation, it is also again more or less a conventional OFDM processing receiver. We are clocking the ADCs at 4 gigasamples per second rate and using a direct conversion receiver architecture in the analog front end. So in-phase and quadrature components are sampled separately into the digital. Then we're doing some filtering, decimation, frame detection, timing acquisition, and frequency offset correction becomes vital because of the use of different oscillators. And there onwards, the conventional OFDM processing blocks, FFT, estimation, equalizer, all these colored blocks have been implemented currently. And this slide shows you how the packet structure can be exploited for packet detection. So the packet detection exploits the short training fields repeating structure, and packet is determined by comparing the autocorrelation and the variance estimate of the incoming signal. So if this ratio is above 0.85, we declare that as a valid packet. And this is a high-level diagram of the digital circuit that is used for detecting a valid packet. It's a similar scenario for the detection flag, and frequency offset estimation is done in two steps: coarse frequency offset estimation and fine frequency offset estimation. So the idea is to exploit again the repeating structure. So when you do this multiplication with the repeating number of samples, then when you accumulate this, the phase that is being accumulated is kind of proportional to the frequency offset. And since we know the number of repeating samples, then by dividing by that, we can get a rough estimate of the sampling offset, the frequency offset estimate. And since we know the sampling frequency, that corresponds to the frequency offset, the actual frequency offset. So the figure shows how this can be done in digital. Fine frequency estimation is also performed the same. Here now the resolution is high because the repetition pattern is, the sample that repeats is much longer here. It's the same procedure, and both coarse and fine estimation needs the implementation of inverse tan2 function, which can be realized through a codic implementation in digital. The timing acquisition is also implemented in a conventional way using a simple match filter. Because we are using 64 subcarrier architecture, it would come down to a 64 tap FIR filter. So if we see the complexity of this FIR filter, because it's a 64 tap, it has a multiplier of 64 times 3 because of the complex valid coefficients. And because of the polyphase architecture, then this gets multiplied by the number of phases. So which comes down to a very high complexity. And to avoid the very high complexity here, the filter coefficients are replaced with its sign magnitude, which makes the filter multiplier less. And we were able to achieve similar performance as of the exact coefficients. So these two peaks corresponds to the two LTF symbols that have been transmitted consecutively, and this less high peak corresponds to the cyclic prefix, which is actually a part of a copy of part of the LTF symbol. The channel estimation and equalization is done through the LTF or the long training field symbols. BPSK symbols are transmitted in the long preamble, and because of the +1 -1 symbols, we can avoid division in the hardware. Equalization is, which I have implemented, is basic zero forcing like equalization, because this is an OFDM system. So this is implemented by multiplying with the conjugate, the division of two complex quantities can be brought down to multiplying the numerator with the conjugate of this, and then doing two real divisions for performing this division. So which is actually illustrated here. And we have implemented these in the FPGA and verified in the loop back mode, looping the DAC I and Q outputs to the ADC inputs. So to verify that digital circuits work. And also now going back to the real-time 4-channel prototype supporting 8 gigahertz bandwidth, we are doing this experiment at B band. So Now this figure shows this 4-channel real-time experiment that we did in the lab. In this case, we are using this high-tech board and using the 8 DACs to bring out 4 baseband channel outputs, and using 4 IQ mixers to upconvert to different IF frequencies. These are some of the oscillators that we use to drive the LOs of the IQ mixers. Here's a wide band combiner that combines all these channels, and that's been sent to the 120 to 140 gigahertz up converter. And here's a PSG that drives the LO input of this up converter, and this is being received here at the 120 to 140 gigahertz down converter, and it is being driven by another keysight PSG, and the output IF output is being viewed at the digital storage oscilloscope. You can see the 4 channels is being transmitted here. And now this is a D-band 4-channel real-time transmission setup. The scope captured waveforms are processed for validating real-time transmission over the air. So going to specifics, the channel multiplexing oscillators are selected to be 3.5, 6, 9.5, and 12.5 gigahertz. Up converter LO here is chosen to be 130 gigahertz. Now this is being illustrated in this frequency diagram. So we have 4 of these baseband channels. I'm just illustrating one, the blue channel here. And let's say it's this first channel, it's being up converted to 3.5 gigahertz. So in the frequency domain, we will see these, I mean, negative and positive symmetric spectrum. Now when we up convert, now we have 4 such different channels, and then we up convert this to 130 gigahertz. And at these particular frequencies, there are not much filters available. Therefore, when this up conversion happens, there are 2 sidebands generated. So there is no means of no way for us to suppress one of the sidebands. Therefore, both of these sidebands have been transmitted. So the upper sideband goes from 132.5 to 143.5 gigahertz, and correspondingly, the lower sidebands also occupy the same bandwidth. And now these 2 bandwidths causes some problems in reception, and to avoid sideband overlapping, we are using a high side LO scheme for bringing down the spectrum to IF, and we are in this case we are using a 146 gigahertz LO, and that brings this guy down to here. And because it's a high side LO, the down converted IF frequencies now become flipped, and that's why I indicated them as negative. And this channel actually comes as a lower frequency here, because we are using this particular 146 gigahertz LO, and you can see that this blue channel that was at 3.5, which was at 133.5, now becomes centered at 12.5, but all the spectrum will be now flipped. And then at the receiver, we are able to sorry. Okay, so at the receiver, we are able to reconstruct the signal by down converting at the specific center frequencies of these channels, and thereby recovering the signal. So we were able to software process these signals. On here are the frequency domain signals that have been transmitted, 4 channels that were multiplexed, and the captures were used at IF to generate the constellations. And here I show 2 of the constellations corresponding to channel 1 and channel 4. We were able to get a EVM of minus 12 dB and minus 11 dB for channel 4. And now over this testing of the full system involving the real-time digital backend, is currently in progress. We are tweaking some parameters to suit the channel conditions. So that kind of concludes my presentation. So in summary, communications at terahertz frequencies has drawn a lot of attention, and significant progress has been made in terms of front-end electronics to enable communication at above 100 gigahertz frequencies. The current wireless research at terahertz frequencies is confined to static wireless links. The devices are ready, communication aspects are being figured out, but it's still not clear how the real-time processing of ultra-broadband signals can be handled, and the ability to real-time process these multi-gigahertz wide bandwidth in baseband is currently holding back the research of real-time links at these particular frequencies. So to close this gap, we advocate an SDR platform using Xilinx RFSoCs, and that is proposed to support the real-time multi-broadband communication over multi-gigahertz of bandwidth at terahertz frequencies. So build a RFSoC-based 4-channel prototype that has been designed and implemented and experimentally demonstrated. I have a special acknowledgement here to my supervisor, Dr. Joseph Janet, the PI of the Ultra Broadband Networking Laboratory, and Dr. Archana Madanayaka, my PhD advisor, for insightful discussions we had during this work, and also Priyanshu Sen, the PhD student that I worked closely for the collaborative work. And also I acknowledge the funding from US Air Force Research Laboratory grant, this particular grant number for the financial support. And these are some references I used. Thank you everyone for listening, and thank you for the University of Moratuwa student branch for again inviting me for this presentation.
Okay, thank
So
you.
I'll be happy to take any questions if you have.
Yeah, thank you very much for accepting our invitations and presenting this state-of-the-art work at the Northeastern University in collaboration with Professor Archana Madanayaka at the FIU. So we have several questions. Actually, the first question is basically what equalization techniques that you use to avoid multipath fading channel effects as mentioned in slide 14. So basically, equalization techniques,
this is, this is single carrier. So this is a zero forcing tap delay equalizer. I think with 10 taps, I guess. I cannot remember.
Okay, yeah. So for the second question, enlighten us about estimated power demands of transmitting, receiving, and processing of such high-frequency bands. Estimated power demands for the transmitting, receiving, and processing of, and how different would that be from current standard? So basically, we had the sub 6 gigahertz, and how the things will change when we move into the above 100 gigahertz, the millimeter waves.
So first of all, like now 5G systems that use millimeter wave has this particular issue of closing the link budget because of the high frequencies, and because of the high frequencies, the antenna sizes are very small. And as I explained, the power density that is intercept to the antenna becomes much smaller. So you will see an effective high spreading loss. So compared to sub 6 gigahertz, you will need much larger number of antenna elements to collect the same power as example for let's say for 2.4 Wi-Fi gigahertz scenario, and to collect the same power as your dipole connects in your Wi-Fi router, you now would need the same aperture to be covered by the number of sufficiently higher number of antenna elements to collect the same power. And on top of that, at these particular frequencies, now the technological devices are still being evolved. So there is not much power supported by devices instantly at these particular frequencies. So that puts a barrier of commercializing these devices for now. But the research is being progressed, and for now, the only way is to have much more higher gain in the antennas, both at transmitter and receiver side, either through fixed gain antennas or higher dimensional antenna arrays.
Okay, so basically with this, I have a question from my side. So basically, so you basically mentioned about the power amplifiers and those kind of things, right? In this frequency. So basically, they have limited power capability.
Mm-hmm.
So you mean this power amplifiers and those components have limited capability at the moment at the 100 gigahertz.
Yes, and power. I mean, there can be cutting edge devices that supports much more power, especially power amplifiers. But now we get to these frequencies by frequency multiplication chains.
Okay, yeah.
So that inherently produces harmonics,
Yes,
and the
yeah.
power will be wasted in those harmonics as well. So
Okay,
there will be much less power at these frequencies.
okay, yeah. So the question 3 is, why does these higher frequency signals get distorted more than regular frequency signals?
I'm not sure why.
So basically, I
What
think
he's
it's with the
asking. Yeah.
signal to noise ratio, or basically this BPSK and the QPSK patterns, they are widely spread, I think.
Oh, I mean, that's because of the. I mean, now we have a lot of components here, and I mean, these chains. I mean, this. I mean, if I have the IF directly going into this up converter, it goes through a certain number of components, and now I have an additional overhead here that has another IF analog network. So all these components have a noise figure, and that contributes to the overall noise figure of the system. So currently, these DACs have a certain power limit, and so to have a certain signal to noise ratio, you will have to have a higher power at the input. So basically, it's the noisy components that's making the constellations look that distorted.
Okay, so these are basically the questions from the audience.